All right, so the next example of finding the inverse of a function is f of x equals 7 over 2x plus 4. So I'm going to go through the same 4 steps that we just talked about. So the first step is just write the function using y instead of f of x. I need to do that because the next step is to switch the x and the y, right? Okay. And now comes the fun part. So step 3 is solve that equation for y. So this is solving this equation for y is an intermediate algebra problem that on a scale from 1 to 10, I would rate about a 6.5. Okay, it's not the easiest problem I've ever done, but it's not that hard. Okay, so this I just, rewrote the equation. Okay, so the first thing I'm going to do is get this 2y plus 4 out of the denominator. All right, I need to get this y by itself, so I'm not going to be able to do that as long as it's sitting down here in the denominator. And the way that I'm going to do that, let me see how much work I showed here. The way I'm going to do that is I'm going to multiply both sides of the equation by 2y plus 4. So let me just scribble a little something on here. I multiplied this side by 2y plus 4. Sorry about that crazy line there. Multiplied this side by 2y plus 4. Okay. So on this side, it cancels the 2y plus 4 and just leaves me with the 7. So that's how I get x times 2y plus 4, like you see here, equals 7. All that's left on the right side is 7. Okay. So again, I'm trying to solve for y. So, and there are actually 2 ways you could go with this. One thing you could do, and I see students do this, and it works, is you could distribute the x. That actually makes the answer at the end come out a little prettier. I did not do it that way. What I did was, again, I'm trying to get the y by itself, so this x is in my way. Why don't we get that x out of there? And the way I'm going to do that is by dividing both sides by x. See what I did there? So I divided this side by x and divided this side by x. Okay, so that y is looking more and more exposed. All right, and that's the point, right? I'm trying to get it by itself. And the rest of this is pretty easy, isn't it? So the next thing I'm going to do is subtract 4 from both sides. Okay. And that gives me what you see there. So minus 4 on this side, minus 4 on this side, right? 2y equals 7x minus 4. And now let me show you ahead of time what I'm going to do to finish it off. So normally the way that you make a 2y into a y is you divide both sides by 2. All right, and that wouldn't be wrong. I'm going to save myself a step. Instead of thinking of it as dividing both sides by 2, I'm going to multiply both sides by 1/2, because then I won't have what we call a complex fraction on the right side. All right, that'll get rid of the 2, just like dividing by 2 would. And it'll make it look like this. Okay, y equals 1/2 times 7 over x minus 4. That is now solved for y. So now the hard part's over. I just write it using the function notation. Oh, that's right. First, I distributed the 1/2. You don't really have to do that, but it makes it look a little nicer. You don't have the parentheses anymore. And now I will write it using the function notation. So the inverse of the function f of x equals 7 over 2x plus 4 is f inverse of x equals 7 over 2x, subtract 2. Okay. This brings us to a way to tell very easily from the graph of a function whether or not it has an inverse. Okay. So let's read this and maybe think a little bit about why this is true. A function f that has an inverse that is a function, I usually just say a function f that has an inverse, a function f has an inverse if there is no horizontal line that intersects the graph of the function at more than one point. So I can't remember if we talked about it in here. I feel like we did. The vertical line test. So the vertical line test is how you tell whether or not something is a function. Whether or not something is a function. Okay. So a function that has an inverse would also pass the horizontal line test. So let me show you why that should be true. Okay. So I have this example. Which of the following graphs represent functions that have inverse functions? So if I click here, I see that there is a horizontal line that intersects this graph in more than one point. And what that previous slide said is that means this function, it is a function because it passes the vertical line test, but it does not pass the horizontal line test, and that means that this function does not have an inverse. So let me show you why that is. Take the 2 points that this line intersects at, and of course they can't make them be nice numbers, so I'm just, okay. Come on now. You know what, I'm just going to use the mouse. All right, so we got 1 point here, and we got 1 point here. So let's say that this point here, I'm just going to pretend that it's -2, 3. I know it's a little off. I really don't want to deal with fractions or decimals. And let's say that this point is 2, 3. Since they're on the same horizontal line, they would have to have the same y coordinate. Okay. Now, there is absolutely nothing wrong with a function taking both -2 and 2 over to the number 3. There is absolutely nothing wrong with that. Okay, we talked about that at some point. Okay, that's perfectly okay. But if this thing were to have an inverse function, look at what it would be trying to do. It would be trying to take the number 3 over to both the numbers 2 and -2. And that is a big no-no. This is not a function, all right? We set our definition of a function, the simplified definition that I like is no 2 ordered pairs have the same x coordinate. So you cannot have both 3, 2 and 3, -2 on the graph of a function. Another way to see that, let's say that I put 3, -2. Let's say 3, -2 is here, and I mean 3, 2, and then 3, -2 would be down here. Well, now those lie on the same vertical line. All right, so that's another reason why that wouldn't be a function. So what the graph that they gave me, it is a function. It is a perfectly good function, but it is not what we call a one-to-one function. And one-to-one functions are the ones that have inverses. So this is a function, but it does not have an inverse. So what about letter B over here? Well, no matter where you draw a horizontal line, it only intersects once. It starts to look a little iffy when you get over here because the graph gets really, really flat over here, all right? But it never becomes perfectly flat. So since there is no horizontal line that intersects this more than once, this function does have an inverse. Okay? This happens to be the graph of what's called an exponential function, and we will talk about those in pre-calc. All right, graphs of f and f inverse. So it happens to be true that the graph of f inverse is a reflection of the graph about the line y equals x. And you're going to see what that looks like here in a minute. The reason that that's true is that if you think about the 4 steps to making an inverse function, step 2 involves switching x and y. Okay. So for example, let's say that the point 2, 3 was on your original function. 3, 2 would be on your inverse function graph, all right? And if you get enough of those points, you start to see that it's mirroring them across the line y equals x. All right, so let's see what that looks like. And I absolutely hate this example, but so far I haven't really gotten motivated enough to change it. The reason I hate this example is because, of course, this function, this is a function, but this is not a one-to-one function, is it? This fails the horizontal line test, all right? I don't think they meant to do that. I think that I just think they didn't think about it very carefully. So we'll pretend we don't notice that, okay? And we'll just talk about what does it look like to draw the graph of F inverse. So I am really going to be putting my pen skills to the test here, okay? I better use the line instead of the, okay. So normally I would make this as a dotted line. I don't know how to do that, so I'm just going to go with this. Here is the line y equals x. Okay. So when you reflect this graph across the line y equals x, here is what it looks like. Ready? So the 0.41 would end up right around the 0.14, and that would make a line that goes all the way over to about the 0.2, -2. So that would be part of it. All right, so what's happening there, let me just point at some things here. This part of the graph of F is getting reflected over here, all right? So for example, the 0.41 on the original function moves over to 1,4 because x and y trade places, right? The -22 on the graph of the original function moves over to 2, -2, okay? And then the rest of this looks like, let's see, it's going to be another line. On the original graph, I have -3, -2, and so this one needs to end up at -2, -3. So it would look something like this. All right, so I'm kind of proud of myself. That red line there would be the graph of F inverse, and I think I have another copy of it over here. Okay, so that brings us to the end of section 1.8. Here's a chance for you to try drawing some inverse function graphs. So here you see the graph of two different functions. Notice that they are both one-to-one. They both pass the horizontal line test. So what I would like you to do if you're watching at home is pause the video and think about what the inverses of these functions would look like. And then we'll come back and compare notes. Okay, let's compare notes. So graph number 1, let's see. I'm not going to draw the line this time because I actually have the inverse all in here. Maybe I'll draw the line after I get it up there. I don't want to mess it up. All right, so your inverse would look something like that, right? Here is the line y equals x, looking something like that. All right, and then graph number 2, that inverse looks something like this. All right, now I had a little mishap with my technology. I could not quite figure out how to do it perfectly, so of course there should be more graph down here. All right, should go all the way down there. Okay, and then the line y equals x is doing something like this. So it is a reflection across the line y equals x. And I have stopped the recording.